Hello, everyone. Welcome back to the structures. And today we're going to be dealing with moment distribution. Basically, as you saw in the thumbnail, we'll be looking at the carryover, factors, the distribution moment, the carryover moment, the relative member stiffness, the member stiffness, and so on and so forth. In this video, I'll make sure that you understand the concepts basically of moment distribution method. And please, if you know that maybe peradventure you've seen my videos before and you loved it, please give this a like button. And also, if you haven't and this is your first time, why not? Please give it a like, subscribe to the channel, and also share to your friends, your colleagues. So let's get into it. So moment distribution method. Now this is a very interesting stuff. Remember, I made emphasis on displacement method for solving indeterminate structures. Displacement method. So apart from slope deflection, we have the MDM, which is the moment distribution method under this displacement method. So I like to think of this moment distribution method as a build-up on slope deflection method, because when we are like deriving some stuffs, you will see that we are using the relations that we derived for the slope deflection method. So basically, this moment distribution method is basically an iterative process. It was formulated by Adicross. The way I normally think, anytime I hear Adicross, I normally think of iteration, because pipe network analysis. Adicross was also so I always think of iteration. So Adicross was the guy. Yeah. So it's an iterative process, unlike the slope deflection method that we use to solve a lot of simultaneous equations. We used to for instance, maybe we have a structure and we have two joints that are free to rotate. This is a fix. It means that we're having two simultaneous equations in order to get the two displacements, which are the two rotations. But for moment distribution method, is so soft that you won't need simultaneous equations. We use tables this time around. We iterate, basically. Iterate. So that's just the first thing I would want us to know before we get into stuff. So let's get into the main stuff now. So now, let's clear everything I've said and let me introduce you to something. Of course, this is MDM, moment distribution method. So once again, the moment distribution method does not use simultaneous equations. We use tables. But before we understand what is going on in those tables, you need to know something. So there are two scenarios you need to keep notes of. The first one is this. Have an inch, and when we have a fix, and mind you, we're still going to be using as a clockwise for positive and clockwise for negative, mind you. So the first scenario is this. You have an inch and you have a fixed. Let's say we're dealing with specifically with A. That is, we're treating A as the near end. If we're dealing specifically with A, we're treating A as the near end and we're treating B as the far end. So if you have this condition where your near end is an inch and your far end is a fixed support, to know something. So if this is the scenario, you need to now know something. Bringing this diagram here again. You need to know something. Once again, if this is the scenario, if this is the scenario, you need to now know something that would, you must understand. Let's say a moment was applied at A. Let's give it a anti-clockwise moment. It was applied at A. Now, of course, for this, the bending moment diagram looks this way. Let me draw a normal straight line. So I just need to draw a vertical line, and let me start with this. So, of course, the bending moment diagram would be like this. Let's say this one was also a negative moment. Let's just say the bending moment diagram is negative. It's a negative bending moment diagram because of this condition that a moment was applied here. Let's say we just have a negative bending moment diagram. Just think of it, something like this. Ordinarily, there's supposed to be a moment here, but let's just assume something. Let me use another arbitrary shape. Let's say the bending moment diagram was like this. It means that my elastic curve diagram would be like this. My elastic curve diagram, since this is a negative bending moment, for negative bending moments, I have a frowning face. That is, my elastic curve will be like this, a frowning face. Do you get? But now, remember that in this place, at this side, we have a fixed end, and at this side, we have an hinge end. So remember, a condition for a fixed end is that there's no slope. So we need to adjust the elastic curve diagram to, to make it to be aligned with that condition. So to show that there's no slope, we have to redraw the elastic curve and put it that there's no slope. Something like this. Where at A, of course, the slope for an hinge end. Remember that this was an hinge and this was fixed. So I just wanted to show you the elastic curve. This is the elastic curve you now have. So once again, the first scenario you have is that the near end is an hinge. Let me copy the elastic curve. Let me copy it. In it. So once again, bringing that first scenario down, that it is an hinge, near end is an hinge, and a moment is applied. So it means that we'll be having this. This diagram, something like this. Exactly. Theta for a moment applied. So once again, this is our first scenario, first case. Now, let's invoke the slope reflection equation. Remember, if this was A and this was B, let's find the expression for the moment here. Of course, the moment here would be equivalent to the moment called MAB. And MAB, which is equals to M, will be equals to 2EI over length, open brackets, 2 theta A. Of course, this is theta A because this point is A, plus theta B minus TB times chord rotation. Now, of course, FEM will be 0. Neglect it rather. So, based on this condition of the beam I'm looking at here, B is fixed and the slope for a fix is 0. So we have theta A remaining. So I don't want to put it as MAB, I want it to be in terms of M. So I remove this MAB, leaving it in terms of M. So 2EI over L, open bracket, 2 theta A. So what does that make it? 4EI theta A over L. Now this M is the formula or is the expression for the moment applied at A, where the near end is inch and the far end is fixed. Near end inch, far end fixed. Once again, it is the moment applied at A. Moment applied at A. You would not really understand this concept of moment applied at A now, but I assure you that when we get to solving more questions rather, you will definitely grasp the concept I'm trying to, explain. When we solve questions, you understand what this applied moment means. You will see it for itself. You will see it for what it is. So this is M, this is the applied moment. So what else do we need to know? Of course, in slope deflection, like we said something that is always a member hand moment. So this one too, it means that at B we also have a moment. We'll call it MBA, not just at A. I'm sorry. Also have a moment. At A we have a moment. So let's do the moment at B now. That is, B is now the near end and A is the far end. There's a difference. Before we did the case that A was the near end and B was the far end. Now we're dealing with B as the near end and A as the far end, which we call MBA. So now MBA would now be equals to 2EI over L 2 theta A, 2 theta B rather, plus theta A. Chord rotation is 0, FEM is 0, so plus 0, no need for that. And from, once again, the diagram, it is obvious that B is a fixed end. So since B is a fixed end, I can put theta B to be 0. Yes. I'm even looking at something. But let me put theta B to be 0. Yes, let me put theta B to be 0. It will make sense. Yes, so we have MBA to be equal to 2EI theta A over L. Yes, this is what I was thinking of. So, if MBA is 2EI theta A over L, and MAB, which is also M, is equal to 4EI theta A over L. What can you see? Can we develop a relationship between MBA and M? Can we develop a relationship between MBA and M? Okay, yes, it is very possible. So to do that, we can say that M is equals to, I can see MBA in M. We just have to multiply it by 2. Can you see? Because M is 4EI theta A over L, but MBA is 2EI theta A over L. So I've seen something, so I can form an expression based on what I've seen. What did I see? So Remember, M is 4EI theta A over L, and that's 2EI over L theta A. This for MAB times 2. Do you get? So 2EI theta A is MBA, rather not MAB, forgive me. So it means that M will be equal to MBA times 2. Do you get? So that is the expression. So now I can say that the moments at BA can be gotten from the moments applied at A. All we just have to do is that we have to just divide the moment applied at A by 2. That is all. We don't need to invoke slope deflection method again. We don't need slope deflection method again, because we know that MBA, the moment at B, at member NB, considering member AB, can be gotten from the moment at A by just dividing the moment applied at that A by 2. Simple, right? So based on this, we can see that there is a factor of multiplication of the applied moment of or at A in order to get the moment at B, considering member AB, that is MBA. And that factor is basically half. MBA is equals to half times M. This factor is called the carryover factor. Now, once again, I would love to recall that the scenario we're dealing with is of this kind. Let me copy it. We're still dealing with this scenario. So it means that if I apply a moment of 150, or let's say 200, where this is an inch. Remember, this must be the condition. This is an inch and this is fixed. It means that half of 200 will be carried over to this place. 100, same direction. So that is just what I'm trying to explain based on this scenario. Now we have another scenario called not more the inch, now the inch, not more the inch fix, but now the inch. So scenario 2, case 2. The cases are always normally combined, but we would look at every one of them first before we start dealing with the combined cases. When they give you a question, it's always combined. So before we deal with the combined ones, we have to break it down first, and that is exactly what I'm doing now. So case 2 now is saying that both ends are inch. Now this is pretty straightforward. Of course, the elastic curve would be like this. Theta B, where this is A and this is B. Once again, the elastic curve is upwards because I have a moment in this direction. Remember that a moment in this direction, if this is my bending moment, would try to pull my bending moment downwards, and if my bending moment is downwards, it means that my elastic curve if this is my beam, my elastic of B is frowning face, and like this. So that's just the concept behind it. So let's continue. M. So case 2, inch. Now, the beautiful thing about this is that we would not even waste time, because normally we know that if not for the fact that a moment was applied here, this moment at A would have been 0. Do you get? So it means that with this, with the same fashion of knowledge, we can say that MB is equal to 0. This is normal analysis. We all know this. So, if this is the case, we can still invoke the slope deflection method, eliminating theta b. Then when I mean eliminating theta b, I mean making theta b subject of formula and substituting it in the formula for MAB, which is basically M. So let's do just that, and you see. So once again, MAB, which is equals to M, is equals to 2EI over L 2 theta A plus theta B. Once again, cold rotation is 0, fixed end moment is 0. Yeah. And now we can see that MBA is equals to 0, is equals to 2EI over L over 2 theta B plus theta A. So if this is equal to 0, then of course our rotations cannot be 0. It will have to be this guy that will be 0. So 0 is equals to 2 theta A, 2 theta B rather, plus theta A. It means that theta B is equals minus theta A over 2. And now we can substitute this. We can substitute inside this equation, saying that is M is equals to 2EI over L 2 theta A theta A minus theta A over 2. So when we have 3EI theta A over L. So it means that the applied moment for this condition where we have inch, where the near end and the far ends are inch, for this condition, the applied moment at this point will be EI theta A over L. Please follow me. A is a subscript, please. Please follow me. Stay with me. So, for this, if the moment here at B, if this is A and this is B, if the moment here is 0, then it means that there is not going to be a transfer of moment. Remember that in the first one, we established a relationship that, okay, when we found MBA with the slope deflection equation, we saw that MBA was actually M divided by 2. So we could establish a relationship. But now we are saying that, okay, with slope deflection method, MB is 0. So the only way M can be equals to MB is when we multiply it by 0. So it means that the carryover factor for this scenario now, that is inch, the carryover factor is 0. The carryover factor is 0. So M is equals to 3EI theta A over L. MBA is equal to 0. So it means that there's no way there's no way we can transfer moment. So carryover factor will be equal to 0. So that is the first thing we should know. Now let's move to member bending stiffness. Bending stiffness. Now, for a hinge fixed, which is the first case, we saw that the moment applied at the near end, where the near end is hinge. Please, this don't mix it up. This scenario is for when the near end is hinge. Near end in the sense that is where you are specifically based on at that instance, where you are concentrated on at that instance. Maybe you are dealing with a distributed moment around that joint. That is around, maybe you're dealing with member AB and you're focusing on member A. Maybe you are busy distributing the moments to member A. So it means that your near end is A and your far end is B. If you are focusing on distributing it to member AB, but you will get all that. But I'm just here to tell you that you should know that these scenarios that we first of all introduce you to has to do with near end and far end. So when I say hinge fixed, I mean hinge is the near end and I mean far end. So MAB, which was our moment applied at the near end, you'll see what I mean very soon. Theta A over L. And MBA, the moment at the far end was 2EI theta A over 2. But we don't even need it. We don't need this. I just want to let us know something. The moment applied. Exactly. So bending stiffness. Let me just give you a simple definition. Bending stiffness is how much moments can be used to cause a unit rotation. That is how much of applied moment. Can you see? Now remember that this is applied. This M is here. This M here is applied moment. Remember I said applied moment. Remember I was discussing applied moment when I said when we apply moments here, then to carry over to the far end, that. So leaving that aside, building upon that knowledge, let me now introduce you to the concept of bending stiffness. So now once again, bending stiffness is saying that how much of applied moment can I apply in order to cause a unit rotation? That is simply bending stiffness. And what is a unit rotation? A unit rotation is setting your rotation to 1. So it means that I can say that my bending stiffness K bar for a hinge fixed is going to be 4EI times 1 over L, which is going to be equals to 4EI over L. Moment applied. You might be thinking, why didn't you put AB or BA? Well, see something. I need you to understand this. If I apply, once again, hinge fix, let's say, of course, yes. So since I'm dealing with applied moments now, and that's why I was trying to remove our eyes from MAB or MBA. Since I'm dealing with applied moments now, right, that I'm applying it to that segment of the beam, and I'm now defining bending stiffness as how much I need to apply in order to cause a rotation of that beam. It means that for that beam, whether it is ABO, whether it is BAO, it means that for that beam, my bending stiffness is just me setting theta A to be 1. Because from the definition of bending stiffness, it is how much of moment can I apply to the beam. To the beam is no end to the beam. So I can have my bending stiffness as KAB, K prime AB, or K prime BA, because I'm dealing with to the beam to cause a unit rotation, a rotation of 1. So that is it. So now we'll be dealing a minute. Now, when we are dealing with a fixed, an hinge now, not an hinge. This is the second scenario. Hinge. This means that my bending stiffness be equals to 3EI over L. You get. So now this is bending stiffness. There's now something called relative stiffness, member stiffness. Relative member stiffness is when your members have the same elastic modulus. If you notice that your member have the same elastic modulus, then no need to be putting E for each of the for each of the members. For instance, maybe I'm dealing with this beam. This is this beam, and this is A, B, C. Okay. If E1 equals to E2, then it makes sense for me to still be using this formula, because and two different separate formulas where there's E, and it makes sense for me to be using any formula that there's E, so that I can account for the E difference. But if my E is now the same, it doesn't make sense for me to be using any formula that has E, that has elastic modulus. So what can I do? There's now something called relative member stiffness. I don't need my E anymore, since all my members have the same E. So what do I need it for? So that is just what relative member stiffness is saying. So it means that relative member stiffness is telling us that we should divide our K prime by 4E. That is by E, but by 4E. In order to eliminate E, because E's are the same now. Do you get? So I will have for relative member stiffness. Similarly, this is K prime. K is 3I. Dividing it by 4, you have this. So with this in mind, we can proceed to the next concept. There's something called distribution factors. Distribution factors. So the concept of distribution factors is just like, okay, let me give an instance. A minute. Distribution factors. Now, let's say we have this beam. let's forget all these parts. Let's forget all these parts. Let's forget these parts. Let's focus on the joints. Well, let's remove the arrow to make it more neat, but forget those parts. Let's focus on the joints. Let's say a moment was applied here. Let's say I apply a moment here. And this, so this part is A and this is C. Now, distribution factor is saying that how can I distribute this applied moment at B to BA and to BC? That is to the end of AB at B and to the end of being portion BC at B. How can I distribute this applied moment? How? That is what distribution factor helps us to do. And it helps us to do that based on the member stiffness, the bending stiffness that we just derived. Without the bending stiffness, it can't distribute. That is, it proportions the distribution based on the stiffness of our member portions. That is just it. That is it. That is it. Please know this. So I won't just say that, okay, if this is M, U, let's say M over 3 go here, and the remaining one, whatever it is, that's 2M over 3. Go here. No. Or rather, let me not put it there, let me not confuse it. I can't just say that M over 3. Since it's member end moment, we're dealing with from transfer of joints, from joints to member end moment. Okay, let me recap. When we are dealing with distribution, we're dealing with distribution from joints to member ends. Do you get? Distribution of joint to member ends. So when I'm saying now distribution moment, it means that there must be a distribution factor to distribute this moment from the applied moment at the joint. This distribution factor would come from on the stiffness of the member portions. So let's say based on the distribution and everything, my distribution moment ended up to be M over 3 at BA and 2M over 3 at BC. Do you get? So I'm just saying that I have joint and I have member connected to the joint, detaching it from the joint. When I distribute the moments here, what would I have in this place? What would I have in this place? That is distribution moment. Now, carryover factor that we now talked about the other time is now saying that, okay, I've distributed you to this place. You have one here. I've distributed you here. Now, let me carry you to this place. Now, carry over 2 based on the second distribution moment. Remember, 2 distribution moments now because we're having 2 things connected to that joint. So, carry over 2 is now saying that, okay, you this distribution moment 2. Let me now carry you over to this place. I remember if, let's say, if this is a fix, that is when we can have half as carryover factor. Do you get? Based on what I've said. But had it been it was an inch and you are distributing the moments here, you won't have anything to be 0. Do you get? Likewise, had it been it was an inch, it will be 0. Remember the condition I stated before above. Inch, no carryover moment. I explained it thoroughly there. You can still go back to check it out. But what I'm saying is that let's say this is the joint for this structure and the moment was applied, distributing it to this guy and to this guy, then carrying it over to this place. It might have a carryover factor, it may not have a carryover factor depending on the case of the portion we are dealing with. It may be inch, it may be inch fix, where now, for instance, our far end is inch and our near end was inch also. So inch, do you get? Likewise, inch here and end here. So that's why. So that's the concept of distribution moment. And for us to do our distribution moments, we would have to get our distribution factors, and the factors depend on our stiffness. That is why we derived the formula for stiffness. So let me explain the concepts more thoroughly. So I'm thinking of, okay, you might skip this video if you wouldn't like the derivation, but I'm about to do a derivation, a very quick one based on our distribution factors. So let's consider a frame. Yeah, let's consider a frame. A frame of this manner. Okay. So a frame. Now, let us now apply a moment. Let's say anti-clockwise, or sorry, clockwise. Let's say clockwise. Fixed. Let's name this A, let's name this B, let's name this C, and let's name this D. So now drawing the elastic curve, of course, if for member AB, if that is the case, it means that, considering this moment at B, this blue arrow, so it was a blue arrow, it means I'll be having negative moment, and our elastic curve would now be like this, something like this. Since we're having negative moment, we'll be having a frowning face. So for elastic curve, I'll be using red. So because of the no slope condition, I can move horizontally, then proceed. Yes. Likewise for BC, detaching it, and since the moment was this guy, I'll be having a positive moment, where my elastic curve will be a smiling face, so no positive, no negative. So it means that I'll be having this for my elastic curve, moving with red once again. Exactly. Likewise for BD, I'll be having a bending moment like this. Let's say this is the axis, this is my Y positive axis. So it means that I'll be having a frowning face for my elastic curve in that direction. So it means that using red once again, I'll be having this. Yes. So that is just it. That's what we should know now. So now we can proceed to business. So of course, with, if I say find summation of moments at joint B, what do you think it would be? Pause a minute and think about the answer. Let's say this is MB. Let's say the moment I apply is MB. Let's say the moment I apply is MB, or let's just put M. Let's put M. Let's just put M. What will be the moment at B? So you should know something. Now, remember that I'm that kind of I'm the counterclockwise guy. I always maybe I think I developed it from Assam Kasumali. I don't know. I'm that guy that loves his counterclockwise direction to always be positive and his clockwise direction to be negative for member end moments. While for joints, it means that due to Newton's law, it means that what was counterclockwise in member end will now be clockwise, and that's why we have a clockwise there. But let me show you something. Let me show you something. So detaching the structure, I'll be having this. Oh, why is it not working? Lol. Wonderful. One note, why are you doing this to me? Yeah, so we get straight to the video. Sorry about that break. So this is our structure. Detached. Are you recording OBS? Yes, you are. So, of course, fix. Fix. Oh no, that side was. So, fixed. So, and remember that even in slope deflection, I always assume that the member end moments are always counterclockwise. I was going to counterclockwise. This is counterclockwise. Clockwise. This is the joints. This is the applied moment I have. Now, don't mistake this applied moment for the moments that are internally normally there, naturally. The applied moment was just what we applied, but there's something else that we deal with. That is due to Newton's law from, let's say this is MBA. Right? This is MBC. And this is MBG. We'll be having also MBE in this manner based on Newton's law. We'll be having MBC also in this manner based on Newton's law. And we'll be having, these ones are natural, it's just based on Newton's law. So if that is the case, it means that we have how many moments at the joint? 1, 2, 3, 4. So it means, and everything is clockwise. So if everything is clockwise, of course, one direction, then we can just say that our sum of moments there at B, once again, is equals to M plus MBA, which was the member end moments, but of course, based on Newton's law, it's already a joint moment automatically, plus MBC plus MBD would now be 0. So I remember MBA, looking at this, where the condition. Now, you should know that when we are dealing with frame structures, I would like us to be thinking of points like this as hinges. Do you get? Think of it as inch because it can rotate and it can translate. Think of it as your normal inch support. Just think of it. Though we have internal hinge, I'm not talking about internal hinge. I'm talking about your normal inch support. Think of it like that. So once we have that in mind, it means that we can think of an hinge here, an hinge here. So it means that this is scenario 1, which we did in the first thing we talked about. This is scenario 1 also, and this is scenario 2. Do you get? So, and because we are applying moment at B, it means that B is the near end in this situation, and A is the far end. Similarly, B is the near end, C is the far end. Similarly, B is the near end and D is the far end. So having this in mind, we can say that MBA is equals to 4EI. I mean, MBA is a first case scenario, and a first case scenario expresses that the moment at the near end, that is moment at B, is equals to 4EI theta over L. Moment at the near end, that is the moment applied, is equals to 4EI theta over L. So because M is equals to what's the name, MBA in this instance, I don't know how best I can say it, but because M is equals to MBA in this instance, do you get? Because B is the near end and A is the far end. So we are saying that it represents the first case scenario where we had hinge fix, and because of that we can say that the moment applied will be equal to 4EI theta over L. But once again, where's the moment applied? The moment applied is at the near end, is at B. So that's why we're saying MBA this time, which is equals to 4EI theta over L. I'm just going in circles, but I believe that you grasp what I'm saying. So once again, let me come down to explain. Now, initially we said we looked at this beam when we were dealing with the first case. So it was an inch. And we said if we apply a moment here, that moment is equals to 4EI theta over L. But this time, this moment you are seeing here, this moment here is now here. So it means that this M is now equals to MBA automatically based on this. MBA based on this automatically. Don't know that I'm communicating. Okay, no. How would I put it? Okay, let me come again. Let's not think of it that way. Now, instead of putting the support there, let me put the supports here. The hinge support. Let me put the hinge support here. And let me put the hinge support here. That is, I kept it in 3 places. I'm also learning as I teach, so I'm sorry. That's one of the loving things about teaching. This is an hinge. So this red shaded parts are hinges. So it means that if this hinge and this moment here represents my applied moment, it means that MBA is my applied moment, and it means that it will be equals to 4EI theta over L, because it is the same thing as saying that B is my near end now and A is my far end. Similarly, for hinge, remember that it is 3EI theta B over L. Now, once again, now we're dealing with B and D now. BD, if B is my near end and D is my far end, it will be 4EI theta over L. Also, do you get? So I can now substitute everything inside this equation, inside this guy. I'm saying that M plus MBA 4EI theta b over L1. Let's say this is L1, this is L2, this is L3, and of course this is I1, the inertia that is dealing with that aspect, I2, and this is I3 also, that being portion, the portions rather, plus MBC now would be 3EI theta, theta B, theta 2, theta 1 over 2 plus 4EI 3 theta B, of course 0. So M is equals to minus, let's bring 4E out, and to be carrying everything here to the other side, carrying to the other side. That's why I have minus, but I'm now bringing 4E out. I'll now have I1. Let me also bring theta B out, I1 over L1 plus let me use green, plus 3I2 over L2 plus I3 over L3. Now, what do these guys represent? Who remembers? Pause and think. So once again, this represents K, which is our relative bending stiffness. Our relative bending stiffness. So wait a minute. Okay. I thought we made a mistake, but let's continue. So M is equals to minus 4E theta B times the sum of all the K's. You get the sum of all the stiffness. The sum of all the stiffness. So it means that theta B is equals to minus M over 4A K. You get exactly. So what else can we do? So I think, yes, now that we have this, we can now go and substitute it back into the equations. Remember, we have MBA, which was equals to 4EI theta over L. Substituting theta B rather, not theta A, theta B. Substituting this theta B inside this equation, you'll be having this 4EI over L minus M over 4E summation of the K's. So you'll be having I over L, 4E cancel 4E, you'll be having I over L times minus M, all divided by all the K's. You get. So I over L on its own is K times negative of the moment times summation K. You get, let's say I over L. Okay, the I over L here is since it's MBA, it was high 1 over L1, high 1 over L1, high 1 over L1, high 1 over L1. If it is I1 over L1, that means we're dealing with K of that particular member AB. So we can either say KAB or KBA, but let's just put K1. Do you get? So doing the orders, doing the same procedure for MBC, we'll be having minus M K2 over summation of K. Doing the same thing for MBG, we'll be having minus M K3 over summation of K. So you will notice something, that we're always having K over summation of K, K over summation of K. Also K over summation of K. What does that K over summation of K mean? Well, that K over summation of K means your distribution factor. It is telling you that to get your distribution factor, that is the factor that tells you how much of moments would be converted from the moment applied on a joint to the moment that will be converted to the member end moment, that is the member attached to that joint. So K1. So let's say we have this structure once again, and this is portion 1, portion 2. So let's say a moment was applied there. So to get the distribution factor for portion 1, we'll use K1 over summation of K. That is, summation of K means K1 plus K2. So this value that we obtain here, will tell us, see, when we split this beam, it will tell us how much of moments would be converted from the one applied at the joint to this place. What would get here? So this value will tell us what we get here. While K2 over K1 plus K2 will tell us what we get here, because we're dealing with portion 2, we're dealing with portion 1. So in essence, your distribution factor is telling you that the stiffness of the member you are dealing with over the summation of all the stiffnesses will give you your distribution factor. All the stiffness is connected to that joint, though, not everything in the beam, connected to that joint. We're dealing with K1 plus K2 because we're connecting member portion 1 and portion 2 together. So that's why we're adding K1 and K2 together. And for, of course, if this is A and this is B, and this is B and this is C, for portion AB, it can be taken as portion 1 because that's what we have been saying. AB is portion 1. So since we are dealing with AB now, we can say that the distribution factor, the moment that will be going from the one applied at the joint to member AB at B, the factor that we can use to determine that moment will be K1 over K1 plus K2. That's just what I'm trying to say. So I hope we understand this video. I hope you understand. Please don't forget to share this video to your friends if you helped you. And please, if you have questions, reach out to me in the comment section below. Thank you so much.